Right now, while you're watching this video, something extraordinary is hurtling through space toward our solar system, at speeds that would make your head spin. Scientists have discovered an object moving at 200,000 kilometers per hour, and what they're finding is keeping astronomers awake at night. This isn't just another space rock drifting through the void. This visitor from beyond our solar system is emitting signals that don't match anything we've seen before. Internal illumination that can't be explained by reflected sunlight alone. Harvard researchers are quietly discussing possibilities that would make science fiction writers jealous. The object has been designated Comet 3I Atlas, but that innocent name hides something far more intriguing. Unlike every other celestial body we've encountered, this wanderer is exhibiting behaviors that challenge our fundamental understanding of how cosmic objects should behave. While NASA maintains their standard reassurances about public safety, behind closed doors, the conversations are taking dramatically different turns. Advanced telescopes are detecting emissions patterns that suggest this visitor might be conducting activities we never expected to witness. The most chilling aspect isn't the possibility of invasion or destruction. The real terror lies in a far more subtle scenario. Ether. What if we're being studied? What if this isn't random chance, but calculated observation? Think about how researchers examine laboratory specimens, cataloging behaviors, measuring responses, documenting capabilities. Now imagine that same clinical analysis being applied to our entire civilization by intelligence that operates on scales we can barely comprehend. This represents humanity's first genuine encounter with something that might possess superior knowledge and technology. We have zero understanding of the evaluation criteria being applied to our species. Are we being measured for our scientific advancement, our capacity for cooperation, our potential threat level? The variables being assessed could determine outcomes we're not even capable of imagining yet. The timing feels almost orchestrated. His arrival coincides with our most turbulent period of technological development, environmental crisis, and social upheaval. If advanced intelligence wanted to evaluate humanity during our most revealing moments, they couldn't have chosen a more perfect window. Every decision we make, every response we demonstrate could be providing crucial data about our species' true character and capabilities. Traditional comets follow predictable patterns. They warm up as they approach stellar bodies, releasing gas and dust in organized streams that create those magnificent tails we associate with cosmic visitors. But 3I Atlas is rewriting those rulebooks. Its emissions don't correlate with solar heating cycles. The internal activity appears independent of external energy sources, suggesting mechanisms that operate according to principles we haven't discovered yet. The mathematical precision of its trajectory raises additional questions. Most interstellar objects follow chaotic paths influenced by gravitational interactions with multiple star systems over millions of years. This visitor's course appears remarkably focused, arriving with velocity and direction that will carry it through the most observable regions of our solar system. Coincidence or something else entirely? Ground-based observatories and space telescopes are working around the clock, gathering every possible data point before this opportunity disappears forever. The James Webb Space Telescope has detected unusual spectroscopic signatures that don't match conventional comet composition models. Carbon compounds are present, but arranged in patterns that suggest complex molecular structures rather than simple frozen gases. The European Space Agency's analysis reveals velocity characteristics that challenge standard gravitational models. Objects traveling between star systems typically show evidence of their journey through interstellar space. Radiation damage, surface erosion, compositional changes from cosmic ray exposure over geological timeframes. 3I Atlas displays remarkably pristine characteristics, as if its journey through the galaxy has been carefully protected or recently initiated. What makes this discovery even more significant is our unprecedented ability to observe and analyze interstellar visitors. Previous objects like Oumuamua appeared and vanished before we could deploy our full scientific capabilities. This time, we have months of observation opportunity with our most advanced instruments. Every day brings new data, and every data set reveals additional mysteries that traditional comet models struggle to explain. The social implications are equally profound. This discovery arrives during an era when humanity is actively searching for signs of extraterrestrial intelligence through projects like SETI and breakthrough initiatives. We've spent decades listening for radio signals from distant civilizations. Now we might be facing the possibility that advanced intelligence has chosen to visit us directly, disguised as a natural phenomenon that most people would never question. The scientific community finds itself walking an incredibly delicate line. Too much caution might mean missing the most important discovery in human history. Too much speculation could trigger public panic or undermine legitimate research efforts. Meanwhile, social media amplifies every theory, every rumor, every leaked observation report, creating an information environment where facts and fiction blend into indistinguishable narratives. Government agencies are maintaining their standard protocols while quietly implementing enhanced monitoring procedures. Military satellites are being repositioned for optimal observation angles. Deep space radar installations are tracking movement patterns with unprecedented precision. These responses suggest that official assessments might be taking possibilities seriously that public statements haven't acknowledged. The October approach date represents our best opportunity to gather conclusive evidence about 3i Atlas's true nature. As it passes closest to our Sun, any artificial systems would likely demonstrate increased activity levels. Natural comets would follow predictable outgassing patterns based on solar heating. If this visitor truly represents something extraordinary, the coming weeks will provide the definitive proof that changes everything. Whether this cosmic messenger carries ancient ice from distant star formation regions or represents our first contact with superior intelligence, our response will define how humanity handles its greatest challenge. The universe has delivered a test of our scientific maturity, our capacity for rational analysis under extraordinary circumstances, and our readiness to accept that our cosmic neighborhood might be far more populated than we ever dared imagine. The countdown has begun. In just weeks, we'll discover whether we're alone in the universe or if we've been under observation all along. Unlike typical solar system inhabitants that follow predictable elliptical paths, returning endlessly in cosmic cycles, this wanderer possessed kinetic energy that screamed of impossible distances. The mathematics told a story of journeys spanning light years, carrying momentum from gravitational encounters with alien suns that existed long before Earth formed its first oceans. When detection systems locked onto its position, 3i Atlas was positioned approximately 4.5 astronomical units from our star, maintaining a distance equivalent to Jupiter's orbital radius, roughly 675 million kilometers of empty space separating us from this mysterious traveler. The challenger facing astronomical teams worldwide extended beyond simple observation. This visitor had positioned itself against the star-dense galactic plane, creating a backdrop so brilliant with distant suns that isolating its faint signature required extraordinary technical precision. Every telescope pointed toward its location struggled against overwhelming stellar contamination, yet the global scientific community responded with unprecedented coordination and determination. Within hours of confirmation, the Minor Planet Center activated emergency protocols, broadcasting circular announcements that reached observatories across 6 continents. NASA's Jet Propulsion Laboratory immediately began generating ephemerides, complex mathematical tables that would predict the object's exact position throughout its entire solar system passage. Planetary defense networks at NASA and the European Space Agency deployed their most sophisticated tracking systems, creating real-time monitoring that would continue until the visitor disappeared back into interstellar darkness. The designation process itself reveals the methodical nature of modern astronomical discovery. Initially catalogued under the temporary identifier 11PL3Z, the object quickly earned the designation C/2025 N1 as its cometary characteristics became undeniable. Only after confirming its truly interstellar origins did it receive the historic classification 3-AT-LAS, joining the exclusive roster of confirmed visitors from beyond our cosmic neighborhood. This represents just the 3rd such object in recorded human history, making every observation precious beyond measure. This rapid identification sequence might appear routine to casual observers, but it represents the culmination of decades-long investment in planetary protection infrastructure. The global network that successfully tracked 3i Atlas includes ground-based survey telescopes, space-based observation platforms, and computational modeling systems capable of predicting orbital evolution, with startling accuracy. Within mere days of discovery, astronomical teams possessed precise knowledge of where this visitor would travel throughout its entire solar system encounter. However, this orbital precision itself became a source of intense speculation among researchers studying the data. While 3I Atlas displayed clearly hyperbolic geometry, confirming its unbound trajectory, one characteristic seemed almost impossibly convenient for random cosmic chance. Its orbital path followed a retrograde direction, moving opposite to planetary motion, yet maintained an inclination of merely 5 degrees from the ecliptic plane. This geometric alignment meant the visitor traveled in rough coordination with planetary orbits, a configuration that struck some observers as suspiciously organized for a supposedly random interstellar wanderer. The initial weeks following discovery generated wildly fluctuating estimates regarding the object's physical dimensions and luminosity characteristics. Such uncertainty represents completely normal circumstances for newly discovered comets, positioned at extreme distances, where instrumental limitations and atmospheric interference consistently produce conflicting measurement results. Unfortunately, in our hyperconnected information environment, this standard scientific uncertainty became fertile breeding ground for elaborate speculation and conspiracy theorizing. Every revision of size estimates, every new observation that refined previous conclusions faced intense scrutiny from online communities searching for hidden significance in routine scientific methodology. Amateur astronomers and professional researchers found themselves navigating an unprecedented landscape, where normal peer review processes competed with social media amplification of preliminary results. Throughout this chaotic period, one assessment remained consistently reassuring from NASA's Planetary Defense Coordination Office. The 3I Atlas presented zero threat to Earth's safety. Comprehensive trajectory analysis suggested no possibility of impact scenarios, with the object's hyperbolic path carrying it safely past our planet at comfortable distances measured in hundreds of millions of kilometers. For planetary defense specialists, 3I Atlas represented simply another cosmic visitor requiring cataloging and scientific study, albeit possessing particularly impressive velocity characteristics and unusual trajectory geometry. Their protocols treated it as a fascinating research opportunity, rather than a potential hazard requiring emergency response measures. Yet even as astronomical teams worked methodically to understand this new arrival, something about its behavioral patterns continued generating intrigue and occasional unease among careful observers. The combination of extreme velocity, near-ecliptic trajectory, and precisely timed close encounters with Mars and Jupiter suggested levels of cosmic choreography that challenged purely random explanations for its arrival timing and geometric properties. The visitor's approach trajectory seemed almost engineered for optimal observation opportunities from Earth-based telescopes. Its path would carry it through regions of space, offering maximum visibility windows, while avoiding orbital configurations that might obscure critical observation periods. Such convenient timing raised questions about whether this represented extraordinary coincidence or something requiring more complex explanations. Advanced computer simulations revealed additional intriguing characteristics about 3I Atlas's journey through our solar system. Its velocity vector suggested gravitational interactions with multiple stellar systems over millions of years, yet its current trajectory appeared remarkably pristine, lacking the chaotic perturbations typically associated with extended interstellar travel through regions populated with massive objects. The mathematical models used to predict its future position demonstrated unusual stability and precision. Most interstellar objects show subtle variations in their predicted paths, as new observational data refines orbital calculations. 3I Atlas maintained remarkably consistent trajectory predictions, suggesting either exceptional measurement accuracy or underlying dynamics that followed more predictable patterns than typically expected. As observation campaigns intensified, distinguishing between meaningful patterns and cosmic coincidences would become one of the fundamental challenges in understanding what 3I Atlas truly represented. The boundary between scientific analysis and speculative interpretation began blurring as each new dataset revealed characteristics that simultaneously supported conventional comet models, while raising questions that challenged standard assumptions about interstellar visitor behavior. The stage was set for months of intensive observation, with every telescope on Earth and in space preparing to capture unprecedented data about humanity's third confirmed visitor from the stars. Whether this represented routine scientific opportunity or something far more extraordinary would depend on what those observations ultimately revealed about this enigmatic traveler's true nature and origins. The spectroscopic evidence emerging from multiple space telescopes tells a compelling story about 3I Atlas's composition, yet each revelation raises new questions about what we're truly observing. The simultaneous detection of carbon dioxide and water vapor within the visitor's expanding atmosphere provides strong support for conventional comet models, but the precise ratios and distribution patterns of these compounds reveal characteristics that don't perfectly match textbook examples. Carbon dioxide sublimation occurs at significantly lower temperatures compared to water ice, explaining why this gas dominates the visible coma at 3I Atlas's current solar distance. However, the sheer volume of carbon dioxide being released suggests an internal reservoir that exceeds typical comet compositions. The extended cloud measures over 348,000 kilometers across, equivalent to the Earth-Moon distance, indicating either an unusually volatile-rich nucleus or sublimation processes operating with unexpected efficiency. As this cosmic wanderer continues its inward journey toward late October perihelion, thermal models predict that rising surface temperatures should trigger increased water vapor release. This transition will provide crucial data about the object's internal structure and composition gradients. If 3I Atlas behaves according to standard comet physics, we should observe a predictable shift from carbon dioxide dominance to water vapor prominence as solar heating penetrates deeper into the nucleus. The chemical signatures detected in 3I Atlas's atmosphere reveal fascinating clues about its probable formation environment and subsequent history. Significant carbon dioxide concentrations suggest the object originated in extremely cold regions, precisely matching expectations for bodies that endured millions of years traversing the frigid interstellar medium. During this extended journey, continuous cosmic ray bombardment would have altered surface chemistry, potentially creating the volatile-rich layers we observe during current outgassing episodes. Multiple research teams have attempted reconstructing 3I Atlas's origin story through trajectory analysis and compositional modeling. Various studies propose formation within the galaxy's thin disk or thick disk regions, each possessing distinct stellar populations and chemical characteristics. However, these theoretical models remain highly speculative, and the true birthplace of our visitor may remain permanently beyond scientific determination. Photometric analysis of 3I Atlas's brightness variations provides additional evidence supporting natural cometary processes rather than artificial origins. The measured luminosity changes match expectations for a rotating, sublimating nucleus surrounded by an active dust envelope. Crucially, no observations have detected unexplained brightness anomalies, structured thermal signatures, or other phenomena that might indicate technological systems operating within or around the object. The morphological characteristics revealed by Hubble's high-resolution imaging show a classic teardrop-shaped dust cocoon surrounding the hidden nucleus. This configuration results from the complex interplay between solar radiation pressure, particle dynamics, and orbital mechanics, all operating according to well-understood physical principles. The apparent forward-pointing plume, sometimes described as an anti-tail phenomenon, represents normal behavior for active comets when viewed from specific geometric angles. Yet beneath this seemingly straightforward interpretation, subtle anomalies continue generating discussion among researchers analyzing the data. The brightness concentration observed on the sun-facing hemisphere initially sparked speculation about possible self-illumination or exotic energy sources. However, experienced comet specialists quickly recognized this as likely evidence of dust phase angle effects, an optical phenomenon that can create misleading brightness distributions under certain viewing conditions. The interaction between large dust particles and solar radiation creates extended structures that can appear to point toward the sun when observed from particular perspectives. These formations result from particles too massive for solar wind to easily disperse, creating persistent features that follow different dynamics compared to smaller dust grains. Such behavior represents physics in action rather than mysterious technological processes. Media coverage has frequently conflated coma-size measurements with actual nucleus dimensions, leading to exaggerated claims about the object's physical scale. Early reports suggesting 3I Atlas measured tens of kilometers across almost certainly described the extent of the surrounding gas and dust cloud, rather than the solid body itself. Hubble's careful analysis indicates the actual nucleus measures between 0.32 and 5.6 kilometers in diameter, making it relatively modest in size despite its enormous atmospheric envelope. The volatile composition tells a remarkable story about 3I Atlas's probable journey through space and time. The presence of substantial carbon dioxide reserves suggests formation in environments far colder than typical solar system regions. During its long interstellar voyage, radiation processing would have modified surface chemistry, potentially creating the complex mixture of ices and organic compounds we observe sublimating today. Advanced spectroscopic analysis reveals molecular signatures that provide windows into the object's deep history. The specific isotopic ratios and compound distributions carry information about the stellar environment where 3I Atlas originally formed, potentially billions of years ago in regions of the galaxy with vastly different chemical compositions than our local stellar neighborhood. As monitoring campaigns continue tracking 3I Atlas's approach toward perihelion passage, each new observation contributes crucial data points to our understanding of this remarkable visitor. The combination of gas detections, dust morphology analysis, and brightness behavior creates an increasingly detailed picture of an active comet carrying volatile ices that underwent extensive processing during its lengthy interstellar journey. However, significant questions persist about the exact composition of those ice reservoirs, the internal structural organization of the nucleus, and the detailed mechanisms driving the observed outgassing phenomena. The object's status as an interstellar visitor makes every aspect of its behavior scientifically invaluable, representing our third opportunity to study material that originated beyond our solar system's gravitational boundaries. The emerging consensus from current observational evidence strongly supports the conclusion that we're witnessing active comet physics, rather than technological systems in operation. The detected compounds, thermal behavior, and structural characteristics all align with expectations for ancient ice and rock that has wandered between stars for geological timeframes before encountering our cosmic neighborhood. Nevertheless, the scientific method demands maintaining openness to alternative explanations while extraordinary claims await extraordinary supporting evidence. The boundary between natural phenomena and potential technology becomes increasingly complex when dealing with objects possessing such unusual characteristics and origins. Current data provides compelling evidence for conventional comet processes, but 3I Atlas's unique status as an interstellar visitor ensures that every observation carries implications extending far beyond routine astronomical cataloging. Whether this represents a straightforward example of cosmic ice sublimation or something requiring more complex interpretations will depend on what additional observations reveal during the crucial months ahead. In the landscape of scientific exploration, few academics possess the courage to venture into territories where conventional wisdom fears to tread. Dr. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University and founding director of the Black Hole Initiative, represents precisely this type of intellectual pioneer. When examining 3I Atlas, Loeb and his research collaborators have presented a fascinating possibility that challenges traditional astronomical interpretations and demands serious consideration, regardless of how it might unsettle established scientific perspectives. The fundamental question Loeb poses cuts to the heart of our cosmic assumptions. Could this interstellar wanderer represent technology rather than natural phenomena? His argument constructs itself upon multiple observational characteristics that he considers potentially consistent with artificial origins. The mysterious sun-facing luminosity detected in preliminary reports, the object's trajectory that positions it remarkably close to the ecliptic plane, and its precisely choreographed flyby encounters with Mars and Jupiter, collectively create patterns that, in his assessment, warrant investigation extending beyond purely conventional explanations. The most intellectually provocative aspect of Loeb's analysis involves what he terms a reverse Oberth maneuver scenario. Traditional spacecraft operations utilize the Oberth effect to achieve maximum velocity gains by firing propulsion systems when orbital speeds reach their highest values, typically occurring at perihelion during closest stellar approach. Loeb suggests that sufficiently advanced civilizations might employ opposite strategies, utilizing perihelion passages for deceleration and braking maneuvers by expending thrust precisely when orbital dynamics would render such operations most thermodynamically efficient. This conceptual framework extends into even more speculative theoretical territory through Loeb's discussion of potential mothership and reconnaissance probe configurations. The hypothesis proposes that our observations of 3I Atlas might represent either a scouting device dispatched by a larger interstellar vessel, or potentially a fragment of a massive craft that experienced structural failure during its extended journey between stellar systems. While these concepts remain entirely theoretical, they exemplify the type of unconventional thinking required when confronting phenomena that challenge standard interpretations. Loeb has actively advocated for utilizing existing spacecraft assets to obtain higher resolution observations of 3I Atlas during its scheduled Mars encounter in October 2025 or its projected Jupiter flyby in March 2026. The Juno spacecraft, currently conducting orbital operations around Jupiter, might theoretically be repositioned to capture enhanced imaging during the visitor's passage. Similarly, various Mars orbital platforms could potentially be retasked for intensive study missions. However, the practical feasibility of such observational campaigns remains questionable given complex orbital mechanics constraints and existing mission priorities. The most controversial element of Loeb's technological hypothesis concerns the possibility of autonomous illumination systems. He has suggested that the apparent brightness irregularities observed in 3I Atlas might indicate some form of artificial lighting apparatus or possibly nuclear-powered propulsion mechanisms. This would represent a radical departure from natural cometary behavior, where luminosity variations typically result exclusively from reflected stellar radiation and thermal emissions from heated dust and sublimating gases. To properly evaluate these propositions, we must examine them within the context of Loeb's previous research on interstellar objects. Following Oumua's discovery in 2017, Loeb co-authored scientific papers proposing that the object's unusual acceleration characteristics and absence of visible outgassing might be explained through light sail technology, essentially describing a thin artificial membrane designed for propulsion via stellar radiation pressure. While most researchers have subsequently concluded that natural hydrogen gas outgassing can adequately explain Oumua's behavioral anomalies, the light sail hypothesis generated important discussions about methodologies for recognizing artificial objects within space environments. The scientific community's response to these technological hypotheses has demonstrated mixed reactions, generally trending towards skepticism. Most astronomical observations of 3I Atlas continue supporting conventional cometary interpretations. The detection of carbon dioxide and water vapor compounds, the presence of substantial dust envelope structures, and the morphological characteristics revealed through Hubble observations all correspond naturally with expectations for active comet systems. This analytical framework brings us to a fundamental principle governing scientific methodology. Extraordinary claims necessitate extraordinary supporting evidence. While technological explanations for 3I Atlas's observed behaviors remain theoretically plausible, current observations have failed to detect the characteristic signatures we might anticipate from artificial objects. No structured radio emissions have been identified, no engineered materials appear in spectroscopic analyses, no geometric features emerge from high-resolution imaging campaigns, and no evidence suggests controlled propulsion or navigation systems. Nevertheless, Loeb's willingness to propose these unconventional ideas serves crucial functions within the scientific process. Hypotheses, including highly speculative ones, help guide observational strategies by suggesting specific evidence categories we should investigate. If 3I Atlas were indeed artificial in nature, what particular signatures should we expect? How would thermal emissions differ from natural outgassing patterns? What spectral characteristics might reveal manufactured materials or controlled energy sources operating within the object? Exploring these theoretical possibilities also compels us to confront deeper questions about our fundamental assumptions regarding the search for extraterrestrial life and intelligence. How would humanity recognize truly alien technology? Would such systems necessarily conform to expectations based on terrestrial engineering principles? Advanced civilizations might develop technologies so sophisticated that they become virtually indistinguishable from natural phenomena to our current observational capabilities. The investigation of technological possibilities forces us to examine our own cognitive limitations when interpreting cosmic phenomena. Human technology follows specific design principles based on our understanding of physics and materials science. Alien engineering might operate according to principles we haven't discovered yet, utilizing materials we can't manufacture and achieving effects we consider impossible within our current scientific framework. Loeb's approach also highlights the importance of maintaining intellectual humility when confronting the unknown. Scientific progress often requires entertaining ideas that initially seem absurd or impossible. Many breakthrough discoveries in physics and astronomy began as theoretical propositions that challenged established scientific orthodoxy before accumulating sufficient evidence to gain acceptance. The technological hypothesis provides valuable benchmarks for future observations of 3I Atlas. If artificial systems were operating within or around the object, we might expect to detect structured electromagnetic emissions, geometric patterns in high-resolution imagery, isotopic ratios, suggesting manufactured materials, or thermal signatures inconsistent with natural sublimation processes. For now, the preponderance of evidence strongly favors natural explanations for 3I Atlas's observed characteristics and behaviors. However, Loeb's technological scenarios serve essential functions by expanding our investigative frameworks and ensuring we remain alert to possibilities that might otherwise escape scientific attention during this unprecedented opportunity to study an interstellar visitor. The scientific method achieves its greatest triumph through constructing arguments from multiple independent streams of evidence that converge toward unified conclusions. When examining 3I Atlas's fundamental nature, the natural comet hypothesis receives overwhelming support from observations spanning the entire electromagnetic spectrum. Each individual piece of evidence points toward conventional physics operating according to well-established principles. Combined together, they construct an extraordinarily compelling case for 3I Atlas as a remarkable yet ultimately natural wanderer from interstellar space. The most unambiguous evidence emerges from molecular detections within 3I Atlas's immediate atmospheric environment. Ceph's identification of an extensive carbon dioxide envelope spanning over 348,000 kilometers provides irrefutable proof of active sublimation processes. This represents the direct phase transition of solid carbon dioxide ice into gaseous form as stellar radiation gradually warms the object's surface layers. Such processes constitute fundamental aspects of cometary physics and require no exotic theoretical frameworks for adequate explanation. The James Webb Space Telescope's detection of carbon dioxide signatures through spatially resolved spectroscopy adds crucial independent confirmation to these findings. JWST's unprecedented infrared sensitivity enables identification of molecular signatures with remarkable precision, and preliminary results demonstrate exactly what theoretical models predict for carbon dioxide-rich comets, positioned at 3I Atlas's current solar distance. Morphological evidence provided through Hubble Space Telescope observations carries equal significance in supporting natural interpretations. High-resolution imagery reveals a classic teardrop-shaped dust envelope surrounding an invisible nucleus, a structural configuration that matches theoretical models of cometary activity with extraordinary precision. No geometric irregularities appear in the data, no engineered features emerge from careful analysis, and no structural elements suggest artificial construction processes. Instead, observations reveal the elegant simplicity of physics operating without technological intervention. A small, cold object gradually warming under stellar radiation while releasing stored volatile compounds into surrounding space. Size constraints derived from Hubble observations, indicating a nucleus diameter between 0.32 and 5.6 kilometers, align perfectly with theoretical expectations for interstellar comet populations. Objects within this size range possess sufficient mass to retain volatile ice deposits during extended interstellar journeys, yet remain compact enough that solar heating can drive significant outgassing activity when encountering stellar systems. 3I Atlas's extreme velocity characteristics and hyperbolic trajectory, while unusual by solar system standards, correspond naturally with expectations for objects that have traversed interstellar space across geological timeframes. Computer simulations modeling galactic dynamics demonstrate that objects ejected from distant stellar systems accumulate random velocity components through gravitational interactions with stars, molecular clouds, and other galactic structures. An object exhibiting 3I Atlas's speed and trajectory fits comfortably within theoretical populations of interstellar wanderers. Perhaps most significantly, we can directly compare 3I Atlas with 2I/Borisov, the previous interstellar comet discovered in 2019. Borisov demonstrated exemplary cometary behavior throughout its solar system passage, exhibiting clear compositional transitions from carbon monoxide and carbon dioxide dominance at large distances to water vapor dominance during closer solar approaches. The compositional similarities between 3I Atlas and Borisov suggest we're examining the same fundamental class of objects, ancient chunks of primordial ice and rock that formed around distant stars billions of years ago before wandering into our cosmic neighborhood. The International Monitoring Campaign, studying 3I Atlas, represents a magnificent triumph of collaborative scientific methodology. Hubble provides precise size constraints and detailed morphological analysis. JWST contributes comprehensive spectroscopic identification of molecular species. SPHERICS maps extended atmospheric structure, distributions. Ground-based telescopes contribute photometric monitoring and compositional analysis, while continuously refining orbital predictions through positional measurements. Each instrument addresses different scientific questions, and their combined results paint a remarkably consistent picture of active cometary processes operating according to established physical principles. Persistent confusion in media coverage has resulted from misinterpretation of size measurements reported in preliminary studies. Some reports have described 3I Atlas as measuring dozens of kilometers across, but these measurements almost certainly refer to the extent of surrounding dust and gas atmospheres rather than dimensions of the solid nucleus itself. Hubble Space Telescope's meticulous analysis, which carefully accounts for atmospheric contributions to total brightness measurements, provides much more restrictive constraints on actual object dimensions. The question surrounding 3I Atlas's ultimate origin remains scientifically fascinating, but inherently uncertain given current observational capabilities. Different research teams have proposed formation scenarios within either the galaxy's thin disk or thick disk regions, stellar populations characterized by different ages, metallicities, and chemical compositions. Some theoretical models suggest 3I Atlas could predate our solar system's formation, representing a relic from the galaxy's early epochs of star formation processes. However, these origin models carry substantial uncertainties, and the true birthplace of 3I Atlas may never receive definitive determination through available evidence. The close planetary approaches that have attracted attention in certain analytical circles are actually less remarkable than initial impressions might suggest. Statistical analysis of hyperbolic orbital trajectories demonstrates that numerous random interstellar paths will experience close encounters with major planets simply through chance geometric alignments. The fact that 3I Atlas passes within 0.1, 9 to 0.2, 0 astronomical units of Mars and 0.36 astronomical units of Jupiter reflects the substantial size and gravitational influence of these planetary bodies rather than any intentional targeting or navigation. Ongoing monitoring efforts continue providing strong support for natural comet interpretations. Photometric observations reveal brightness variations entirely consistent with rotating, sublimating nucleus behavior. Spectroscopic monitoring detects precisely the molecular species theoretical models predict from warming cometary ice deposits. Morphological studies identify dust structural features that match computational simulations of cometary activity with impressive accuracy. No current observations require invoking exotic physics or artificial origin hypotheses. As 3I approaches its late October perihelion passage, we can formulate specific predictions based on natural comet theoretical frameworks. Water vapor signatures should become increasingly prominent as surface temperatures rise above sublimation thresholds for water ice deposits. Dust production rates should increase substantially, potentially rendering atmospheric features more visible to ground-based observational campaigns. The nucleus may demonstrate fragmentation signatures if thermal stresses exceed structural integrity limits. These predictions are testable and specific, providing clear methodologies for validating or challenging natural comet interpretations through future observations. If 3I Atlas were artificial in nature, we might anticipate fundamentally different behavioral patterns. Stable brightness characteristics unrelated to solar distance variations, absence of volatile molecular signatures, or geometric features visible through high-resolution imaging campaigns. Current scientific consensus strongly supports treating 3I Atlas as a natural, albeit remarkable, example of interstellar comet populations. Its carbon dioxide-rich composition provides unprecedented insights into environmental conditions around distant stellar systems billions of years ago. Its successful preservation of volatile ice deposits during extended interstellar travel illuminates fundamental physics governing small body evolution within galactic environments. Whether 3I Atlas ultimately proves to represent an exotic natural object or reveals unexpected anomalies requiring revised theoretical frameworks, our careful study exemplifies science operating at its most fundamental level: patient accumulation of evidence, rigorous testing of competing hypotheses, and willingness to remain surprised by whatever revelations the universe chooses to provide. Understanding why 3I Atlas has generated such profound interest and occasional panic requires examining the peculiar psychological mechanisms that govern human responses to celestial phenomena. Our cognitive architecture evolved across millions of years to navigate terrestrial dangers, yet it displays systematic biases when confronting the infinite scales and alien physics that characterize space environments. These mental shortcuts shape not merely individual reactions, but the collective discussions that emerge around enigmatic astronomical visitors. Psychologists have documented a phenomenon termed dread risk, minus our inherent tendency to overestimate both the probability and severity of catastrophic yet statistically unlikely events. This cognitive shortcut provided significant survival advantages for our ancestors when evaluating threats from predators or environmental disasters, but it creates systematic distortions when applied to astronomical phenomena. A comet that presents zero actual danger can nevertheless trigger intense anxiety simply because it represents an unknown variable from an incomprehensibly vast universe beyond our control. The effect heuristic compounds this psychological tendency by directly linking emotional responses to risk evaluations. Events that generate feelings of fear automatically receive higher danger assessments, regardless of objective evidence contradicting such conclusions. When confronted with something as fundamentally alien as an interstellar visitor traveling at 200,000 kilometers per hour, our emotional warning systems activate long before rational analysis can provide mathematical reassurance about safety margins. Ambiguity functions as another powerful amplifier of fear responses. During initial weeks following 3I Atlas's discovery, when orbital parameters remained uncertain and spectroscopic analysis was still incomplete, the absence of definitive information created cognitive vacuums that speculation rushed to fill. Humans evolved in environments where unidentified threats could prove lethal, so our default response to ambiguous situations involves heightened vigilance rather than patient curiosity or scientific skepticism. Modern media ecosystems can transform these individual psychological tendencies into collective phenomena that operate at societal scales. The 24-hour news cycle demands constant content generation, and uncertainty surrounding cosmic visitors provides fertile ground for sensational narratives that capture attention more effectively than measured discussions of orbital mechanics and spectroscopic analysis methodologies. We can observe this pattern clearly by comparing media coverage of 3I Atlas with official communications from NASA and the European Space Agency, where headlines emphasize terms like mystery object, blazing speed, and unknown visitor. Scientific institutions focus on specific measurements, distances, velocities, chemical compositions, and trajectory predictions. Identical factual information generates completely different emotional responses depending entirely on how it's presented to public audiences. The precedent established by Omi Wamo illustrates how these psychological dynamics evolve over extended timeframes. Initial observations revealed an object with unusual properties, elongated geometry, absence of visible atmospheric features, and slight acceleration that couldn't be explained through gravitational forces alone. In the absence of immediate explanations, speculation flourished, including hypotheses about artificial origins and extraterrestrial technology. Only after months of careful analysis did the scientific community converge on natural explanations involving hydrogen outgassing from processed water ice deposits. Understanding these psychological patterns helps explain why planetary defense communications emphasize concrete, measurable facts rather than interpretative speculation. When NASA announces that 3I Atlas will pass no closer than 1.8 astronomical units from Earth, this specific distance measurement serves multiple important functions simultaneously. It provides precise quantitative information for scientific analysis, offers concrete reassurance about safety margins, and demonstrates the accuracy and reliability of our tracking systems to public audiences. Interviews with psychologists specializing in existential threat perception reveal fascinating insights about why cosmic visitors trigger such profound psychological responses. These objects activate what researchers term archetypal fears, deep, culturally embedded anxieties about invasion, judgment, and cosmic insignificance that appear consistently across human societies throughout history. The mere possibility that we might not be alone in the universe challenges fundamental assumptions about our place in creation and our significance within cosmic hierarchies. Yet focusing exclusively on fear responses misses a crucial counterpoint: the extraordinary capacity for wonder that cosmic discoveries can inspire in human consciousness. The same psychological systems that generate anxiety about unknown threats can also produce awe at the magnificent scales and elegant physics revealed through interstellar visitors. 3I Atlas offers unprecedented opportunities to witness material from distant stellar systems, to study chemistry that formed billions of years ago around alien suns, and to glimpse the cosmic processes that shape our entire galaxy. This capacity for wonder serves important functions beyond mere emotional satisfaction. Scientific literacy and public support for space exploration correlates strongly with feelings of cosmic curiosity rather than cosmic dread. When people view astronomical discoveries as opportunities for learning rather than sources of existential threat, they demonstrate greater likelihood of supporting research programs that expand our understanding of universal phenomena. The global collaboration required to study objects like 3I Atlas demonstrates humanity operating at its collective best. Within hours of discovery, observatories across multiple continents began sharing data, coordinating observations, and constructing comprehensive models of the object's trajectory and composition. This response showcases not merely our technical capabilities, but our species' remarkable capacity for cooperation when confronted with cosmic mysteries that transcend terrestrial political boundaries. We can apply these insights to develop improved approaches for communicating about future astronomical discoveries. Media literacy becomes crucial, learning to distinguish between peer-reviewed scientific analysis and preliminary speculation, understanding differences between uncertainty and danger, and recognizing how framing effects shape our emotional responses to information. Risk assessment for 3I Atlas illustrates these principles perfectly. When we compare the actual risk posed by this interstellar visitor, essentially zero Mings, with known impact hazards from solar system objects, we observe that our attention and concern are dramatically misaligned with actual statistical probabilities. NASA's Planetary Defense Coordination Office tracks thousands of near-Earth objects that pose far greater mathematical risks than any interstellar visitor. Yet these mundane solar system residents generate significantly less public interest or emotional response. Perhaps most importantly, we can recognize how our initial emotional responses to cosmic discoveries need not determine our final judgments. Fear naturally narrows perspective, encouraging focus on threats and worst-case scenarios rather than opportunities and potential benefits. Wonder expands perspective, inviting exploration of possibilities and appreciation for the magnificent complexity of the universe we inhabit. 3. This invites both psychological responses, but ultimately rewards the latter approach. Whether it proves to be an exotic natural comet or reveals unexpected properties requiring revised theoretical frameworks, this visitor offers humanity an opportunity to demonstrate scientific maturity the ability to face the unknown with curiosity rather than dread, to seek understanding rather than retreat into comfortable assumptions. As we continue monitoring 3i Atlas's journey through our solar system, we're not merely studying an astronomical object, we're conducting an experiment in how our species responds to contact with the truly alien. The results of that experiment will shape not just our understanding of this particular visitor, but our preparedness for the cosmic discoveries that await us in the decades ahead. Millennia before telescopes unveiled the true nature of comets, human civilizations gazed upward with profound mixtures of reverence and terror, as these unexpected celestial visitors appeared suddenly against familiar stellar backdrops. These cosmic wanderers challenged ancient assumptions about celestial order and divine intentions, triggering responses that echo remarkably in our contemporary reactions to 3i Atlas. Ancient Chinese astronomers designated these phenomena broom stars, believing they swept away ruling dynasties while heralding dramatic political transformations. Imperial court astronomers maintained meticulous observational records of their appearances, creating documentation that modern scientists now utilize to reconstruct historical orbital patterns with extraordinary precision. These ancient observations represent some of humanity's earliest systematic scientific data collection, demonstrating our species' enduring fascination with cosmic visitors. The most culturally embedded example of cometary terror appears immortalized in the Bayeux Tapestry, where Halley's comet blazes ominously across medieval skies above terrified English nobles in 1066. Contemporary chroniclers depicted armed warriors pointing at the celestial visitor with expressions of absolute horror, interpreting its appearance as divine condemnation of King Harold's claim to the English throne. For Norman invaders, however, the identical comet represented favorable supernatural intervention, a celestial sign that God blessed William the Conqueror's military campaign. This dual interpretation reveals profound truths about human psychological patterns. We consistently perceive cosmic events as confirmations of pre-existing beliefs and anxieties, rather than independent natural phenomena operating according to universal physical laws. The comet itself remained unchanged throughout these contrasting interpretations, following identical gravitational principles that govern all celestial mechanics. Only human cognitive frameworks transformed it into either harbinger of doom or herald of victory. Indigenous Australian Aboriginal communities developed extraordinarily rich traditions surrounding cometary appearances that varied dramatically between different tribal groups and geographic regions. Many cultures associated these visitors with death or malevolent supernatural entities, perceiving them as tears in the cosmic fabric or signals of approaching catastrophe. The Wardaman people of the Northern Territory described certain comets as ancestral spirits traveling between sacred locations, while other groups interpreted them as warnings about violations of traditional laws or environmental imbalances. These diverse cultural responses illuminate why fear mechanisms activate so readily when strange objects materialize in our skies. Across vastly different societies and historical epochs, humans consistently interpreted unexpected celestial events as meaningful rather than random, as signs requiring interpretation rather than phenomena demanding systematic investigation. This pattern suggests psychological roots extending far beyond rational threat assessment into fundamental aspects of human cognition. The mechanisms through which cometary omens propagated through ancient societies bear striking resemblance to how astronomical discoveries disseminate through modern social media networks. In medieval Europe, news of celestial apparitions traveled along trade routes and through religious institutions, often arriving weeks or months after initial sightings. By the time information reached distant communities, it had been filtered through multiple interpretative frameworks, embellished with local cultural meanings, and merged with existing folklore traditions. Today's digital networks accelerate this process exponentially, while preserving its essential character. A telescope in Chile detects an unusual object, and within hours, speculation about its nature spreads across continents, faster than scientific analysis can provide definitive answers. The identical psychological drives that led medieval chroniclers to interpret comets as divine messages now manifest as viral theories about alien technology or cosmic threats. The printing press revolutionized how comet panic could spread, but simultaneously introduced corrective mechanisms that hadn't existed previously. Multiple information sources could be compared and contrasted. Authorities could face questioning, and alternative interpretations could compete for public attention through published works. The emergence of scientific institutions like the Royal Society created new frameworks for evaluating celestial phenomena based on systematic observation rather than tradition or religious authority. Modern institutions attempt fulfilling similar stabilizing roles in contemporary contexts. The International Astronomical Union, NASA, and the European Space Agency provide authoritative sources for astronomical information using standardized communication protocols specifically designed to minimize public misunderstanding and prevent panic responses. When these organizations announce that 3i Atlas poses zero threat to Earth, they draw upon centuries of hard-earned experience in distinguishing between genuine hazards and merely unusual phenomena. Yet underlying human tendencies to fill uncertainty gaps with dramatic narratives remain as psychologically powerful as ever. In the absence of complete information's Po2 and complete information about cosmic visitors typically requires months or years to develop, our minds default to pattern-seeking behaviors that served our ancestors effectively in terrestrial environments, but can mislead us when applied to astronomical scales. Historical records reveal that comet panics follow remarkably predictable patterns, regardless of specific cultural contexts. Initial sightings generate uncertainty and widespread speculation. Authorities attempt providing reassuring explanations while acknowledging legitimate unknowns. Popular imagination fills those information voids with culturally relevant fears, divine punishment in religious societies, foreign invasion during periods of political instability, technological threats in our current era of rapid scientific advancement. What makes our contemporary situation simultaneously more challenging and more hopeful than previous historical periods is the democratization of information access. Anyone with internet connectivity can examine identical orbital data, spectroscopic measurements, and imaging results that professional astronomers utilize to study 3 Atlas. The Minor Planet Center's database, NASA's Solar System Dynamics website, and observatory press releases provide unprecedented transparency about discovery and analysis processes. This accessibility creates opportunities for genuine scientific literacy that medieval peasants or even educated nobility could never have imagined. Citizens can learn distinguishing between preliminary observations and peer-reviewed conclusions, understand differences between scientific uncertainty and genuine danger, and participate in collective processes of making sense of cosmic discoveries. The enduring human pattern across all these historical examples involves our tendency to transform astronomical events into stories about ourselves. Ancient Chinese astronomers perceived comets as reflections of imperial virtue or corruption. Medieval Europeans interpreted them through frameworks of Christian theology and feudal politics. We view 3i Atlas through interpretive lenses shaped by science fiction narratives about alien contact and existential risks to human civilization. This pattern isn't necessarily problematic in itself. Narrative frameworks help us process experiences that exceed our normal conceptual boundaries. The crucial element involves learning to hold these stories lightly as provisional interpretations rather than definitive truths, and maintaining openness to revision as evidence accumulates. Perhaps the most encouraging aspect of our modern approach to cosmic visitors involves the remarkable speed with which international collaboration emerges. Within days of 3i Atlas's discovery, observatories worldwide began sharing data, coordinating observations, and constructing comprehensive analytical models. This response demonstrates our species' extraordinary capacity for cooperation when confronted with genuinely cosmic scales and timelines that dwarf terrestrial political divisions. 3. Atlas represents a contemporary test of these ancient psychological patterns. Will we succumb to identical fear-driven narratives that transformed every historical comet into an omen of catastrophe? Or can we develop new cultural frameworks that embrace cosmic visitors as opportunities for wonder, learning, and international collaboration? The answer will be written not in stellar configurations, but in our collective response to this stranger currently racing through our solar system at unprecedented velocity, carrying secrets from distant suns, and challenging us to transcend the evolutionary limitations of our psychological inheritance. Before 3I Atlas commanded our attention, with its extraordinary velocity and carbon dioxide signatures, two previous interstellar wanderers provided essential lessons about how such objects behave and how humanity responds to their presence. Oumuamua, discovered in 2017, and 2I/Borisov, found in 2019, established fundamental baselines for understanding interstellar populations, while demonstrating the critical importance of patient, methodical analysis in distinguishing between genuinely anomalous phenomena and merely unfamiliar physics operating in exotic contexts. Oumuamua arrived first and immediately shattered expectations about what interstellar visitors should resemble. Initial observations revealed an object possessing extremely elongated geometry, roughly 10 times longer than its width, combined with unusual tumbling rotation that suggested either highly irregular form or perhaps flattened, pancake-like structure. Most perplexing, Oumuamua displayed no visible atmospheric envelope or tail, despite exhibiting measurable non-gravitational acceleration as it departed our inner solar system. This combination of characteristics sparked intense scientific debate and inevitable speculation about artificial origins. The absence of visible outgassing seemed to eliminate conventional cometary explanations for the observed acceleration, leading certain researchers to propose that Oumuamua might represent fragments of alien technology, perhaps a light sail engineered for propulsion via stellar radiation pressure, or debris from some unimaginably ancient spacecraft that had wandered between stars for geological timeframes. Dr. Avi Loeb, whose technological hypotheses regarding 3I Atlas we examined previously, co-authored influential research papers proposing the light sail scenario as a scientifically viable explanation for Oumuamua's properties. This represented careful analysis rather than wild speculation. If an object demonstrates acceleration without visible mass loss, and if that acceleration follows patterns consistent with radiation pressure dynamics, then artificial origins become legitimate scientific hypotheses worthy of thorough investigation. However, the scientific community's response to extraordinary claims followed predictable patterns of extraordinary skepticism. Multiple research teams worked systematically to develop natural explanations for Oumuamua's behavior, focusing particularly on possibilities of invisible outgassing that might escape detection through telescopic observations. The breakthrough emerged through detailed modeling of how interstellar radiation affects small object composition across millions of years. Cosmic rays and stellar ultraviolet radiation can systematically break down water ice molecules, creating trapped hydrogen gas reservoirs within object interiors. When such bodies approach stellar systems, warming surfaces can release this hydrogen in quantities too minimal to create visible cometary activity, yet sufficient to produce measurable acceleration effects. Recent analysis published in Nature strongly supports this hydrogen outgassing model, providing natural explanations for all of Oumuamua's unusual characteristics. The elongated shape might result from tidal forces during close stellar encounters throughout its journey. The unusual rotation could reflect complex torques from asymmetric outgassing patterns, and the invisible acceleration corresponds perfectly with hydrogen emission rates predicted through radiolysis theoretical models. 2I/Borisov, discovered by amateur astronomer Gennady Borisov at his personal observatory in Crimea, provided a completely different template for interstellar behavior patterns. From initial discovery moments, Borisov exhibited textbook cometary properties, prominent dust envelope, clear evidence of outgassing activity, and spectroscopic signatures revealing familiar volatile compounds consistent with solar system comet populations. As Borisov approached perihelion during late 2019, detailed spectroscopic monitoring revealed fascinating compositional evolution patterns. At large solar distances, carbon monoxide and carbon dioxide dominated outgassing signatures, exactly matching predictions from sublimation physics for objects existing in extremely cold environments. As solar heating intensified, water vapor began dominating spectral features, following patterns identical to those observed in native solar system comets. Borisov's nucleus proved relatively small, probably measuring less than 1 kilometer in diameter, yet it produced dramatic cometary activity that rendered it easily visible through ground-based telescopes. Mass loss rates measured throughout its solar system passage matched theoretical predictions for objects possessing high volatile content, confirming that interstellar comets can preserve substantial ice reservoirs during extended journeys between stellar systems. Perhaps most significantly, Borisov's behavior demonstrated that interstellar objects need not be exotic or mysterious phenomena. This visitor behaved exactly like comets formed within our own solar system, suggesting that fundamental physics of planetary formation, the accretion of ice and rock in cold, distant regions surrounding young stars, operates similarly throughout our galaxy. The crucial lesson from comparing Oumuamua and Borisov involves recognizing that interstellar objects don't constitute a single category with predictable properties. Some, like Borisov, represent familiar physics operating in unfamiliar contexts. Others, like Oumuamua, challenge our understanding and require years of careful analysis to explain through natural processes. 3I Atlas, with its prominent carbon dioxide emissions and substantial dust envelope, initially appears much closer to the Borisov template than the Oumuamua enigma. CEBEREX and James Webb Space Telescope detections of volatile outgassing provide immediate evidence for active cometary processes, while Hubble's morphological observations reveal classical dust cocoon structures consistent with natural comet behavior. However, 3I Atlas's velocity is significantly higher than either previous interstellar visitor, and its trajectory bringing it unusually close to planetary orbital planes add elements of mystery requiring careful investigation. We learned from Oumuamua and Nube unusual properties don't automatically imply artificial origins, but they do demand thorough analysis before confidently ruling out exotic explanations. Technological advances since 2017 have dramatically improved our capabilities for studying interstellar visitors. When Oumuamua appeared, the James Webb Space Telescope hadn't launched, and SFAH remained in development phases. Ground-based spectroscopy provided limited compositional information, and even Hubble's observations faced constraints from the object's small size and rapid motion through our detection systems. Today's instrumental suite, Hubble for morphological analysis, JWST for detailed spectroscopic identification, SFAREX for extended atmospheric mapping, and increasingly sophisticated ground-based facilities, provides unprecedented capability for real-time analysis of visiting objects. We can detect molecular species that would have remained invisible to previous telescope generations, map spatial distributions of gas and dust with remarkable precision, and track compositional changes as objects evolve throughout their solar system passages. This enhanced capability makes 3I Atlas's approach period particularly exciting from scientific perspectives. Instead of waiting months or years for definitive analysis, we can construct comprehensive models of composition, structure, and behavior within weeks of discovery. The importance of rapid follow-up cannot be overstated, as interstellar visitors represent temporary phenomena, typically visible for only a few months before disappearing back into cosmic void. Future survey systems, particularly the Vera Rubin Observatory's Legacy Survey of Space and Time, promise revolutionizing interstellar object science by detecting dozens or potentially hundreds of such visitors annually. This statistical sample will allow understanding typical properties and behaviors of interstellar populations, making individual anomalies like Oumuamua seem less mysterious and potentially artificial in nature. As 3 Atlas continues approaching perihelion, we carry accumulated wisdom from Oumuamua and Borisov, patience in analysis, skepticism toward extraordinary claims, and appreciation for the remarkable physics governing small objects wandering between stars throughout our galaxy's vast expanses. Among the most captivating aspects of 3I, Atlas's journey lies what certain observers have labeled its suspiciously organized geometry. The object travels along a retrograde orbital path, moving contrary to planetary motion directions, yet maintains a trajectory position merely 5 degrees from the ecliptic plane, that imaginary disk containing most planetary orbits. This near-perfect alignment, combined with precisely choreographed close encounters with major planets, creates patterns that challenge purely random explanations and demand deeper scientific scrutiny. The mathematical precision tells an extraordinary story of cosmic orchestration. The 3 Atlas will approach within 0.19 to 0.20 astronomical units of Mars on October 3, 2025, representing roughly 28 to 30 million kilometers closer than Mars's own moon. Phobos maintains to its parent planet. The Jupiter encounter scheduled for March 16, 2026, brings this visitor within 0.36 astronomical units, approximately 54 million kilometers, of our solar system's gravitational giant. Earth receives the most distant approach at roughly 1.8 astronomical units during December 2025, yet even this safe passage represents a precisely calculated flyby rather than random cosmic wandering. Could such geometric precision result from intentional targeting by advanced civilizations operating beyond our current technological comprehension? This question deserves rigorous examination, but requires careful analysis of what constitutes coincidence in astronomical contexts and how selection effects might distort our perceptions of statistical significance. To properly evaluate whether 3I Atlas's planetary encounters represent genuine anomalies, we must establish baseline expectations for random interstellar trajectories through computational modeling. Computer simulations can generate thousands of hypothetical hyperbolic orbits, featuring various inclinations, orientations, and entry velocities, then calculate what percentage experience close planetary encounters through pure chance mechanisms. Results from such analyses reveal that our solar system's architecture renders planetary encounters significantly more common than intuition suggests. Jupiter and Saturn, possessing enormous gravitational spheres of influence, can deflect or capture objects from considerable distances across space. Mars, despite its smaller dimensions, orbits within regions where numerous hyperbolic trajectories naturally converge through gravitational dynamics. Statistical probabilities of incoming interstellar objects experiencing close encounters with multiple planets reach levels that no longer require exotic explanations beyond conventional celestial mechanics. Moreover, we must account for observational selection effects that systematically bias our sample toward objects possessing interesting characteristics. Survey systems like those that detected 3I Atlas are specifically optimized to identify objects in particular sky regions, especially areas near the ecliptic plane where most solar system activity occurs. An interstellar visitor with orbital inclination far from the ecliptic might pass through our solar system completely undetected, never appearing in astronomical catalogues, despite representing equally valid examples of interstellar populations. Recovery data that extended 3I Atlas's observation arc backward to May 2025 provides crucial constraints on any design trajectory hypothesis. The object's path became established through multiple independent observations spanning several months, reducing degrees of freedom available for fitting intentionally engineered trajectories. The more data we accumulate, the more difficult it becomes to argue that observed trajectories were artificially constructed rather than naturally determined through gravitational interactions. The near-ecliptic inclination that initially appeared suspicious becomes less remarkable when considered within galactic context. Interstellar objects frequently approach from directions related to our galaxy's disk structure, and the ecliptic plane of our solar system roughly aligns with this galactic disk geometry. Objects streaming inward from typical galactic directions naturally tend to intersect our solar system near the ecliptic plane, more often than from completely random directions throughout three-dimensional space. Furthermore, phase angle optical effects creating 3I Atlas's apparent sunward luminosity can be fully explained through conventional dust physics without invoking artificial illumination or propulsion mechanisms. Anti-tail phenomena occur regularly in natural comets when large dust grains too massive for solar wind to disperse efficiently create structures appearing to point toward the sun when viewed from specific geometric perspectives. However, rigorous scientific methodology requires identifying falsifiable predictions that could distinguish between natural and artificial explanations through future observations. If 3I Atlas were indeed a reconnaissance probe or technological artifact, we might expect observing specific signatures that natural objects cannot produce stable narrowband spectral emissions, characteristic of artificial energy sources, structured repetitive radio signals, indicating communication or navigation systems, or non-Keplerian motion patterns, suggesting controlled propulsion or course corrections. To date, no observations have detected any such technological signatures. Radio spectrum monitoring around 3I Atlas reveals only background noise typical of space environments. Its motion follows gravitational predictions with precision expected from celestial mechanics calculations. Spectroscopic signatures match those of sublimating combustices rather than exotic energy sources or manufactured materials. Human tendency toward apophenia perceiving meaningful patterns in random data provides important psychological context for evaluating apparent coincidences. Our cognitive architecture evolved in environments where pattern recognition offered survival advantages, leading us to identify meaningful relationships, even in genuinely random phenomena. When confronted with rare cosmic events, we naturally seek explanations involving intention, design, or significance, rather than acknowledging pure chance mechanisms. This tendency becomes particularly pronounced when dealing with events occurring on astronomical scales and timelines exceeding normal human experience. The concept that an interstellar object could wander our galaxy for millions of years, then happen to pass through our solar system during the brief period when human civilization developed technology to observe it, feels almost impossibly coincidental. Yet vast scales involved render such apparent coincidences statistically inevitable across cosmic timeframes. Monte Carlo simulations that challenge these intuitions reveal fascinating insights about orbital dynamics and probability theory. By generating thousands of random hyperbolic trajectories and calculating planetary encounter statistics, we can determine what percentage would experience close approaches comparable to 3I Atlas's encounters. Results typically demonstrate that such encounters occur with sufficient frequency to require no special explanations beyond gravitational physics. More sophisticated analyses can examine correlations between different orbital elements, whether objects with specific inclinations tend toward particular encounter geometries, or whether certain entry velocities predispose visitors to multiple planetary flybys. These studies help distinguish between genuinely anomalous properties and natural consequences of gravitational dynamics in multi-body systems. The upcoming Mars encounter in October 2025 offers excellent opportunities to test various hypotheses about 3I Atlas's fundamental nature. If the object were artificial, we might expect its trajectory showing subtle adjustments during the Mars flyby, course corrections optimizing its subsequent Jupiter encounter, or adjusting departure trajectories. Natural objects should follow purely gravitational paths determined by their masses and velocities without deviation. Whether 3I Atlas represents remarkable natural phenomena or something far more extraordinary, this study demonstrates the importance of quantitative analysis in evaluating apparent coincidences. The answer may ultimately lie not in stellar configurations, but in our growing sophistication as a species capable of rigorous statistical thinking about astronomical phenomena that challenge everyday understanding of probability, causation, and cosmic significance. As we venture deeper into 3I Atlas's scientific enigma, we confront a fundamental question that has propelled astronomical discovery for centuries. When faced with unusual observations, should we invoke exotic new physics or investigate whether familiar physics operating under extraordinary conditions can explain what we witness? Scientific history suggests that mundane explanations, when carefully analyzed, often prove more illuminating than speculative alternatives, though occasionally genuine revolutionary discoveries emerge from apparent anomalies. Natural explanations for 3I Atlas's behavior commence with its composition, which appears dominated by carbon dioxide-rich ices that sublimate readily as the object approaches our stellar system. This carbon dioxide dominance at large heliocentric distances perfectly matches theoretical predictions for objects that formed in extremely frigid environments and spent millions of years traversing interstellar space, where only the most volatile compounds remain easily sublimatable under minimal thermal energy. Ferrix mission's detection of an extended carbon dioxide cloud spanning hundreds of thousands of kilometers provides direct observational evidence for this sublimation process. As stellar radiation gradually warms 3I Atlas's surface layers, solid carbon dioxide transitions directly from crystalline ice to gaseous form, creating the expanding atmospheric envelope we observe through our most sophisticated instruments. The James Webb Space Telescope's spectroscopic confirmation of these carbon dioxide features adds independent verification to this straightforward physical explanation rooted in established thermodynamics. Water signatures remain relatively weak in current observations, but this pattern aligns perfectly with sublimation physics principles. Water ice requires significantly higher temperatures than carbon dioxide to transition from solid to gaseous phases, so we anticipate water vapor emissions strengthening as 3-eyed Atlas approaches its late October perihelion passage. This represents a testable prediction that will either validate or challenge natural cometary physics through future spectroscopic monitoring campaigns. The intriguing possibility of radiolysis processed hydrogen provides another natural explanation that draws direct parallels to the Oumuamua mystery that captivated astronomers previously. Over geological timescales in interstellar environments, cosmic radiation systematically breaks down water ice molecules, creating trapped hydrogen gas reservoirs within object interior structures. When stellar heating warms surface materials, this hydrogen can escape in quantities too minimal to create visible outgassing signatures, yet sufficient to produce subtle dynamical effects. This radiolysis model successfully explained Oumuamua's mysterious acceleration characteristics without requiring artificial propulsion systems or exotic physics. While 3-eyed demonstrates clear evidence of visible outgassing that renders such invisible acceleration mechanisms unnecessary, the underlying physics demonstrates how seemingly exotic behavior can result from well-understood processes operating across cosmic timescales. Dust grain physics offers another avenue for natural explanations of 3 Atlas's unusual brightness distribution patterns. Large dust particles positioned near the nucleus can create complex optical effects when illuminated by stellar radiation. Depending on particle sizes, compositions, and spatial distributions throughout the atmospheric envelope, dust clouds can produce brightness concentrations that appear to point toward our sun. The apparent forward glow that initially attracted attention as potentially artificial illumination. These anti-tail phenomena are extensively documented in solar system comets, where radiation pressure and gravitational forces create intricate dust structures that can produce counterintuitive appearances when viewed from specific geometric perspectives. No exotic physics or artificial illumination systems are required to explain such features, just the complex interplay between dust dynamics, radiation pressure, and orbital mechanics operating according to established physical principles. The question of 3 Atlas's ultimate cosmic origin adds another layer of natural complexity worthy of consideration. Different research teams have proposed formation scenarios in either our galaxy's thin disk or thick disk stellar populations, characterized by different ages, metallicities, and kinematic properties. These distinct environments would subject forming objects to dramatically different thermal histories, cosmic ray exposure levels, and chemical processing conditions throughout their development. Thin disk origins might suggest a relatively young object formed around a metal-rich star, similar to our Sun, while thick disk origins could indicate an ancient wanderer that predates our solar system's formation by billions of years. The compositional clues that might discriminate between these scenarios remain uncertain, but they illustrate how natural astrophysical processes can produce objects with exotic properties through perfectly conventional physics operating under extreme conditions. Recent orbital analysis published in Astronomy and Astrophysics has refined 3-eye Atlas's trajectory calculations, confirming its extreme hyperbolicity in barycentric coordinates. Manner's measurements relative to our solar system's center of mass, rather than the Sun alone. This analysis underscores the object's genuinely interstellar pedigree, while providing increasingly precise predictions for its future motion throughout the remainder of its solar system encounter. The concept of unknown astrophysical processes deserves careful consideration in any comprehensive analysis. Our understanding of cometary physics, interstellar chemistry, and small body evolution continues evolving as new observations challenge existing theoretical models. 3-eye Atlas might exhibit behavior requiring refinements to current theory without necessarily invoking artificial explanations or exotic physics beyond our current comprehension. However, the scientific principle of Occam's razor suggests we should exhaust natural explanations before considering more exotic alternatives. Unknown natural processes, while certainly possible, represent less radical departures from established science than conclusions that we're observing alien technology. The burden of proof for extraordinary claims rests with those proposing them, not with those defending conventional interpretations based on established physics. This burden of proof framework helps establish clear criteria for evaluating future observations of 3I Atlas throughout its remaining solar system passage. If natural contrary processes explain the object's behavior, we should continue observing spectroscopic signatures consistent with sublimating volatiles, morphological features matching dust and gas dynamics, and thermal emissions correlating with solar heating patterns. Conversely, artificial explanations would predict dramatically different observational signatures, engineered materials and spectroscopic analysis, geometric structures inconsistent with natural erosion processes, energy emissions exceeding solar heating contributions, or controlled trajectory modifications, violating purely gravitational motion principles. The peer review process will play crucial roles in evaluating any anomalous findings as they emerge from ongoing monitoring campaigns. Extraordinary claims about 3I Atlas's nature will face intense scrutiny from the international astronomical community, requiring independent confirmation and thorough analysis before gaining scientific acceptance. This process serves as an essential filter between preliminary observations and established conclusions. Science progresses through such tests of competing hypotheses, where observations serve as arbitrators between different theoretical frameworks. The exotic ice hypothesis, that 3I Atlas represents a natural but compositionally unusual object, processed by millions of years of interstellar wandering, currently provides the most comprehensive explanation for all observed properties. This interpretation requires no physics beyond our current understanding, makes testable predictions about future observations, and aligns with comparative studies of other interstellar visitors. Whether 3I Atlas proves to be exotic ice or something far stranger, its study exemplifies the scientific method operating at its finest: careful observation, rigorous analysis, and willingness to follow evidence wherever it leads, while maintaining appropriate skepticism toward conclusions that would revolutionize our understanding of the cosmos. In the realm of scientific thought experiments, few scenarios capture imagination quite like first contact with extraterrestrial intelligence. While 3LS shows no signs of artificial origin or communication attempts, exploring how humanity might respond to such a discovery reveals critical gaps in our preparedness for potentially transformative cosmic encounters that could reshape our understanding of our place in the universe. Consider this hypothetical scenario. Tomorrow morning, radio telescopes detect a structured, clearly artificial signal emanating from 3I Atlas's position, transmitting patterns that could only result from intelligent design. What happens next would test every protocol humanity has developed for managing extraordinary discoveries that transcend normal scientific procedures. The first hours would challenge verification systems designed for mundane astronomical discoveries. According to SETI post-detection principles established by the International Academy of Astronautics, the detecting observatory would immediately begin intensive verification procedures, confirming the signal's reality through multiple independent observations, ruling out terrestrial interference sources, eliminating equipment malfunction possibilities, and excluding natural phenomena that might mimic artificial transmissions. These verification steps, mundane as they might appear, would prove crucial in preventing false alarms that could trigger premature public panic or inappropriate government responses. The scientific community learned hard lessons from past incidents involving pulsars, initially mistaken for alien beacons, and fast radio bursts that seemed too structured to be natural phenomena. Extraordinary claims about extraterrestrial contact demand extraordinary verification before public announcement. Simultaneously, the detecting institution would notify key international organizations according to established protocols that have never been tested under genuine first contact conditions. The International Astronomical Union serves as the primary coordinating body for astronomical discoveries, while the United Nations Office for Outer Space Affairs provides frameworks for international cooperation in space-related matters. Both organizations maintain contact lists and communication procedures designed for rapid dissemination of critical information, but these systems were designed for conventional discoveries rather than civilization-altering revelations. The Outer Space Treaty of 1967, despite being written decades before SETI became a serious scientific discipline, establishes principles that would guide international responses to confirmed extraterrestrial contact. The treaty's emphasis on peaceful uses of outer space, avoidance of harmful contamination, and international cooperation provides legal foundation for coordinated response efforts, though its frameworks assume human actors rather than alien intelligence. NASA's Planetary Defense Coordination Office, despite its primary focus on natural impact hazards, would likely assume central roles in managing public communications about any confirmed alien contact. The office has established procedures for risk assessment, trajectory analysis, and public messaging that could adapt to communication scenarios. The key difference would involve managing not physical danger, but psychological and social impacts of confirmed contact with non-human intelligence. National security agencies worldwide would inevitably become involved in any confirmed contact scenario, though the balance between security concerns and scientific transparency would prove extraordinarily delicate. Intelligence services might attempt detecting additional signals, analyzing transmission characteristics for technological insights, or assessing potential threats to national interests. However, the international nature of astronomical research and global implications of contact would pressure governments toward transparency and cooperation rather than unilateral secrecy. The existing Mars orbital assets and Jupiter missions that some researchers have suggested for studying 3 Atlas would face immediate retasking pressure if the object began signaling. Spacecraft already positioned near the object could potentially serve as relay stations, signal amplifiers, or close-range observation platforms. However, technical feasibility of such operations would depend heavily on orbital mechanics, communication capabilities, and specific characteristics of any detected signals. The Rio scale and San Marino scale, developed by SETI researchers to quantify significance and implications of potential extraterrestrial contact, would provide frameworks for assessing the importance of any signals from 3 Atlas. These scales consider factors such as signal verification confidence, information content, and potential societal impact, helping officials communicate discovery significance to both scientific communities and general public audiences. Perhaps the most challenging aspect of confirmed contact would involve the question of response protocols. Who, if anyone, speaks for humanity? Current international frameworks lack binding agreements on this fundamental question that could determine our species' first impression on cosmic neighbors. SETI post-detection protocols recommend against any response transmissions until thorough international consultation occurs, but these guidelines carry no legal authority and might prove difficult to enforce under practical circumstances. The democratic deficit in cosmic communication protocols reflects broader challenges in global governance structures. While the United Nations provides forums for international cooperation, its consensus-building processes might prove too slow for scenarios involving time-sensitive communication opportunities or rapidly evolving contact situations requiring immediate decisions. Cultural and religious communities worldwide would grapple with fundamental questions about humanity's place in creation and our relationships with other intelligent beings. Major world religions have developed various theological positions on extraterrestrial life possibilities, but actual confirmation of intelligent non-human technology would test these frameworks in unprecedented ways that no theological scholarship has adequately prepared for. Educational systems would face immediate demands for curricula addressing extraterrestrial contact, astrobiology, and implications of cosmic citizenship. The generation of children growing up after confirmed contact would inhabit fundamentally different conceptual universes than previous generations, with implications extending far beyond scientific education into philosophy, ethics, and social organization. Economic implications of confirmed extraterrestrial technology discovery could prove as significant as political and social consequences. Financial markets might experience extreme volatility as investors attempt pricing the implications of contact with superior technology. Industries ranging from aerospace to telecommunications might face sudden obsolescence or unprecedented opportunities, depending on the nature and accessibility of any discovered technologies. The psychological impact on individual humans would vary dramatically based on cultural backgrounds, religious beliefs, and personal worldviews. Some would experience existential crisis as fundamental assumptions about human uniqueness collapse. Others might feel profound wonder at confirmation that we're not alone in the universe. Mental health systems would need preparation for counseling people through what might represent the most significant paradigm shift in human history. Yet all these speculative scenarios depend on crucial premises that current evidence does not support: that three-eye atlas represents technology rather than natural phenomena, and that any hypothetical artificial intelligence would choose to communicate with us. The carbon dioxide emissions detected by FEREX, dust morphology observed by Hubble, and spectroscopic features identified by JWST all point toward conventional cometary activity rather than artificial systems. This thought experiment serves important functions nonetheless. By examining our preparedness for extraordinary discoveries, we identify gaps in international frameworks, communication strategies, and decision-making processes that might prove crucial in future scenarios. Whether Three-Eye Atlas proves to be remarkable natural ice or reveals unexpected properties, our response will test not just our scientific instruments, but our wisdom as a species standing at the threshold of cosmic awareness, preparing for whatever revelations the universe may choose to share with us. For now, Three-Eye Atlas continues its journey as a messenger from distant stars, carrying ancient secrets while challenging us to expand our understanding of the magnificent cosmos we call home. The possibility, however remote, that interstellar wanderers like Three-Eye Atlas might represent technological artifacts from alien civilizations compels us to confront one of the most profound questions in astrobiology. If we ever discover evidence of extraterrestrial technology, what would such a revelation tell us about the fate of intelligence throughout our universe? The answer touches upon one of the most sobering concepts in modern science, the Great Filter hypothesis, and could fundamentally reshape our understanding of humanity's cosmic destiny. The Great Filter represents a theoretical explanation for the Fermi paradox, that apparent contradiction between high statistical probability of extraterrestrial civilizations and our complete absence of evidence for their existence. According to this hypothesis, there exists some incredibly difficult evolutionary step that prevents most life from reaching technological maturity capable of galactic expansion. This filter might lie behind us, suggesting we're extraordinarily fortunate to have navigated through it successfully. Alternatively, it might lie ahead of us, indicating that technological civilizations typically destroy themselves before spreading throughout galactic environments. If interstellar probes like Three-Eye Atlas actually represented remnants of extinct civilizations, they would provide sobering evidence that the Great Filter lies in our future rather than our past. Advanced species might regularly develop technology needed to explore distant stellar systems, only to succumb to technological self-destruction, environmental collapse, or other existential risks before establishing permanent galactic presence. Such discoveries would transform our understanding of intelligence from cosmic blessing to cosmic curse. Dr. Avi Loeb and other researchers have argued that discovering alien artifacts would fundamentally reset humanity's priorities regarding space exploration, existential risk mitigation, and long-term survival strategies. If other civilizations have risen and fallen throughout galactic history, leaving only scattered technological debris as evidence of their existence, it would suggest that technological intelligence faces systematic challenges we have yet to understand or overcome. However, critics note that this interpretation requires accepting extraordinary claims without extraordinary supporting evidence. The absence of confirmed alien artifacts means we're still operating within speculation rather than established scientific fact. Natural explanations for interstellar objects like Three-Eye Atlas, Oumuamua, and Borisov remain more consistent with current observations than hypotheses involving alien technology or cosmic archaeological remnants. The natural interpretation of these cosmic visitors already provides profound insights into universal processes and planetary formation throughout our galaxy. Borisov's familiar chemistry demonstrated that fundamental physics of planetary formation missioned the accretion of ice and rock around young stellar systems operates similarly across different cosmic environments. Three-Eye Atlas's carbon dioxide-rich composition adds crucial details to this picture, revealing how different stellar environments can produce objects with dramatically varying volatile content and chemical signatures. This growing catalogue of interstellar visitors offers unprecedented windows into planetary science beyond our solar system boundaries. Each object carries chemical fingerprints revealing conditions around its birth star, isotopic ratios constraining formation timescales, and structural properties illuminating billions of years of thermal and dynamical evolution. These insights advance our understanding of galactic ecology without requiring exotic explanations or revolutionary physics. Yet the possibility of technological artifacts among interstellar populations raises important questions about detection methodologies and statistical analysis techniques. A galaxy filled with natural interstellar debris could effectively camouflage artificial objects, rendering them difficult to identify through conventional astronomical observations. This possibility emphasizes the importance of developing instrumental signatures capable of distinguishing manufactured materials from natural compositions through advanced spectroscopic analysis. The search for such technological signatures parallels ongoing efforts in SETI research to identify artificial signals against backgrounds of natural cosmic radio emissions, just as radio astronomy has developed sophisticated techniques for recognizing structured transmissions amid cosmic noise. Optical and infrared astronomy might need developing new methods for identifying technological materials, geometric regularity, or energy sources inconsistent with natural processes operating under known physics. The philosophical implications extend beyond questions of detection methodology to fundamental issues about intelligence and cosmic evolution patterns. If technological civilizations regularly emerge throughout our galaxy only to face systematic existential risks, it would suggest that intelligence itself might represent a maladaptive evolutionary strategy on cosmic timescales. The same cognitive capabilities enabling tool use, scientific discovery, and space exploration might also predispose species towards self-destructive behaviors that ultimately limit their cosmic longevity. Alternatively, discovering evidence of successful long-lived civilizations would provide encouraging proof that technological species can overcome existential risks and establish sustainable galactic presence. Such discoveries would fundamentally alter our approach to long-term planning, space exploration priorities, and risk mitigation strategies for preserving human civilization across cosmic timescales. The brief window during which 3i Atlas remains accessible to our solar system creates tremendous pressure for comprehensive analysis before this opportunity disappears forever. Whether this visitor ultimately proves to be remarkable natural phenomena or reveals unexpected properties requiring revised theoretical frameworks, our scientific response demonstrates growing maturity as a species beginning to take seriously our responsibilities as cosmic citizens. Media management represents another critical challenge requiring unprecedented coordination between scientific institutions, government agencies, and international organizations. Primary goals include preventing public panic, countering misinformation campaigns, and ensuring accurate information reaches global audiences faster than speculation and conspiracy theories can spread through social media networks. Economic markets would likely experience extreme volatility as investors attempt assessing implications of confirmed extraterrestrial contact. Financial systems built on assumptions of terrestrial isolation might face fundamental challenges, requiring entirely new frameworks for understanding value, progress, and technological development within cosmic contexts. Religious and philosophical communities would confront perhaps the most profound implications of confirmed contact with non-human intelligence. While major world religions have developed various theological positions on extraterrestrial life possibilities, actual confirmation would test these frameworks in unprecedented ways that centuries of theological scholarship haven't adequately prepared for. Educational systems would face immediate pressure developing curricula addressing cosmic citizenship and humanity's place within populated universe scenarios. The generational impact cannot be overstated. Children growing up after such discoveries would inhabit fundamentally different conceptual universes than previous generations, with implications extending from career choices to philosophical perspectives we can barely imagine. As 3i Atlas continues its hyperbolic trajectory through our solar system, carrying secrets from distant suns while challenging us to expand our cosmic perspective, we stand at a remarkable threshold. Whether this messenger proves to be ancient ice from alien stellar systems or something far more extraordinary, our careful scientific response reflects humanity's growing wisdom in confronting the infinite mysteries that surround us. The universe has delivered a test of our scientific maturity, our capacity for international cooperation, and our readiness to accept that our cosmic neighborhood may hold surprises beyond our wildest imagination. Whatever revelations await us in the data still being collected, one truth remains certain. We are no longer alone in wondering about our place among the stars. The cosmos itself has become our teacher, and 3i Atlas our latest profound lesson in the magnificent complexity of the universe we call home. As we approach the conclusion of our journey through 3i Atlas's scientific mystery, the moment has arrived to step back and examine the evidence with clarity that emerges from comprehensive analysis. When we compile observations from Hubble's morphological studies, JWST's spectroscopic investigations, and SFERIX's compositional mapping, a remarkably consistent picture crystallizes before us. We are witnessing a natural comet carrying volatile-rich ice and dust from distant stellar systems, representing one of the most extraordinary examples of cosmic wandering ever documented. The carbon dioxide and water vapor detections provide unambiguous evidence of active sublimation processes, requiring no exotic explanations beyond established physics. The teardrop-shaped dust envelope revealed through Hubble imaging matches theoretical models of cometary activity with extraordinary precision that validates decades of computational modeling. Nucleus size constraints measuring between 0.32 and 5.6 kilometers in diameter align perfectly with expectations for objects capable of preserving volatile ices during millions of years of interstellar journeying through the cosmic void. This convergence of independent observations demonstrates science operating at its most powerful level, multiple instruments operated by different teams using distinct methodologies, all reaching compatible conclusions about 3 Atlas's fundamental nature. No single observation would prove definitive by itself, but the cumulative weight of evidence constructs a compelling case for natural rather than artificial origins that grows stronger with each new data set. The contrast between journalism's demand for novelty and science's commitment to accuracy illuminates why preliminary speculations about alien technology gained such prominence in early coverage periods. News cycles require fresh angles and dramatic narratives, often emphasizing the most exotic possible explanations before peer review and archival recovery data can provide more measured conclusions based on rigorous analysis. This tension between media timescales and scientific timescales reflects fundamental challenges in communicating cosmic discoveries to public audiences. The most accurate information emerges gradually through careful analysis, cross-validation, and peer review processes. While public interest peaks immediately following initial discovery announcements, definitive conclusions often emerge after attention has shifted to newer mysteries and sensational headlines. The international collaboration characterizing 3i Atlas research demonstrates humanity's remarkable capacity for cooperation when confronted with genuine cosmic mysteries that transcend terrestrial boundaries. The Minor Planet Center coordinated global observations within hours of discovery. NASA and ESA shared telescope time and data without institutional barriers. University teams worldwide contributed specialized expertise in orbital dynamics, spectroscopy, and compositional analysis, without regard for national affiliations. This collaborative spirit transcends political divisions that often dominate terrestrial affairs, suggesting that cosmic encounters might serve as catalysts for broader international cooperation on challenges requiring global coordination. When faced with phenomena that dwarf human timescales and challenge terrestrial perspectives, our species demonstrates inspiring capacity for collective scientific endeavor that points toward our potential for addressing other planetary-scale challenges. The educational implications of 3i Atlas's study extend far beyond astronomical knowledge into fundamental understanding of cosmic processes. The object's carbon dioxide-dominated composition teaches us about volatile survival in interstellar environments, planetary formation processes around distant stars, and chemical diversity existing throughout our galactic neighborhood. These insights advance understanding of cosmic chemistry while providing tangible connections between abstract astrophysical theories and observable phenomena. The sophisticated instrumental ecosystem enabling real-time analysis of 3i Atlas represents decades of investment in space-based astronomy infrastructure. Hubble's optical imaging capabilities, developed across 30 years of orbital operations, provide morphological insights impossible from ground-based telescopes. JWST's infrared spectroscopy, representing cutting-edge detector technology and precision pointing systems, identifies molecular species with unprecedented sensitivity levels. FIREX's wide-field mapping capabilities reveal extended structures that single-pointing observations might miss entirely. This instrumental network exemplifies how long-term scientific investments pay dividends in unexpected ways. Telescopes designed for studying distant galaxies and exoplanet atmospheres adapt seamlessly to analyzing interstellar visitors, demonstrating interconnected nature of astronomical research and the value of maintaining diverse observational capabilities for addressing unforeseen discoveries. For amateur astronomers and citizen scientists, 3i Atlas offers observing opportunities connecting backyard telescopes with cutting-edge research efforts. While the object remains too faint for easy detection without specialized equipment, experienced observers with larger telescopes and sensitive cameras might capture images during favorable viewing windows. These observations contribute to global monitoring efforts while providing personal connections to genuine cosmic exploration. The mission concepts emerging for closer study of 3i Atlas MS potential observations by Juno during Jupiter encounter or Mars orbiters during October flyby illustrate how existing space assets can be repurposed for new scientific objectives. These proposals demonstrate flexibility of modern spacecraft operations while highlighting importance of rapid response capabilities for studying transient phenomena that appear without warning. However, the real significance of these mission concepts lies not in technical feasibility, but in their demonstration of humanity's growing sophistication in cosmic exploration. We now routinely operate spacecraft throughout the solar system, maintain communication networks across interplanetary distances, and coordinate complex observation campaigns involving multiple space and ground-based assets with remarkable efficiency. The cultural transformation represented by our response to 3i Atlas deserves recognition alongside scientific achievements. Instead of interpreting this cosmic visitor as omen of disaster or divine judgment, we've approached it as opportunity for learning and discovery. This shift from fear-based to curiosity-based responses to celestial events represents genuine progress in human intellectual development that our ancestors would find remarkable. Process transparency, characterizing 3i Atlas research with observations, data, and analysis, freely shared through international databases, demonstrates how open science accelerates understanding while building public trust in scientific institutions. Citizens can examine identical orbital data, spectroscopic measurements, and imaging results that professional astronomers use in their research, participating directly in cosmic discovery processes. This democratization of astronomical data creates educational opportunities previous generations could never have imagined. Students can download real observational data, perform independent analysis, and reach their own conclusions about cosmic phenomena. The gap between professional research and public engagement continues shrinking as data access improves and analysis tools become more accessible to general audiences. Looking toward the future, 3i Atlas provides templates for how humanity might approach subsequent interstellar visitors with greater wisdom and preparation. Rapid response protocols developed for this object, international coordination mechanisms, and multi-instrument observation strategies will serve as models for studying future cosmic messengers that inevitably await discovery. As this remarkable visitor continues its hyperbolic trajectory toward interstellar space, carrying secrets from distant suns, while challenging us to expand our cosmic perspectives, we stand transformed by the encounter. Whether 3i Atlas ultimately proves to be exotic ice from alien stellar systems or reveals unexpected properties requiring theoretical revisions, our scientific response reflects humanity's growing maturity in confronting infinite mysteries surrounding us. In the end, 3i Atlas compels us to confront a profound truth about our cosmic situation that transcends any single astronomical discovery. We represent a young species, barely a few 100,000 years old, observing chunks of ancient starlight and primordial ice, drifting past our tiny oasis within an ocean of space and time, spanning billions of years across trillions of kilometers. This perspective, humbling though it may be, represents one of humanity's greatest intellectual achievements, the ability to comprehend our place within a universe far grander than our ancestors ever dared imagine. Even if 3I Atlas proves to be merely a natural comet, the quotation marks surrounding that description reveal the poverty of such diminutive thinking. Nothing remains ordinary about material that formed around distant stars, survived millions of years wandering the interstellar void, and now graces our telescopes with chemical signatures, revealing processes that occurred billions of years ago in stellar environments we may never personally visit. The carbon dioxide and water vapor we detect today began their cosmic journey when the universe itself was younger, when different constellations illuminated galactic skies, when Earth's biosphere existed in radically different forms than the world we currently inhabit. This temporal perspective fundamentally transforms our understanding of what constitutes extraordinary versus mundane phenomena within cosmic contexts. By universal standards, the emergence of technological civilization on Earth represents an event far more remarkable than the routine passage of interstellar debris through our solar system. Intelligence capable of constructing telescopes, launching spacecraft, and deciphering chemical compositions of objects from distant stellar systems has emerged only recently in cosmic history, and perhaps occurs only rarely throughout our galaxy's vast expanses. If future observations somehow revealed that 3I Atlas represents technology rather than natural ice, the focal series a new kopitain vidapitindane, the vendibnabatorm the firstragon, taught yet scientific honesty, requires acknowledging humanity would face the most profound paradigm shift in our species' intellectual history. We would need reimagining our cosmic context, our long-term survival strategies, and our responsibilities as members of a universe populated by intelligence beyond our own. Such a discovery would immediately activate international treaties, coordination protocols, and communication frameworks we examined throughout our investigation. More importantly, it would test our wisdom, our capacity for cooperation, and our ability to respond to cosmic-scale challenges with appropriate gravity and careful consideration. However, the reality check threading through all such speculation remains crystal clear. Earth will pass no closer than approximately 1.8 astronomical units from 3 Atlas during December 2025. At closest approach, this visitor will remain roughly 270 million kilometers away, equivalent to the distance between Earth and Mars during their nearest orbital alignment. We face zero physical danger from this object, regardless of its ultimate nature or composition. This safety assurance allows approaching 3I Atlas with pure scientific curiosity rather than existential anxiety. We can study this visitor as we would any cosmic phenomenon, seeking to understand its properties, origins, and behavior without urgency that might cloud judgment if it posed actual threats to our planet or civilization. This luxury of dispassionate analysis represents a triumph of human intellectual development. Our ancestors interpreted comets as harbingers of doom precisely because they lacked scientific frameworks needed to assess actual risks versus imagined dangers. We possess those frameworks today, along with technological capabilities needed to track, study, and understand cosmic visitors with unprecedented precision. Humility enforced by cosmic perspective serves important functions beyond mere intellectual honesty, recognizing that our understanding remains incomplete, that surprises await us among stars, and that the universe operates according to physical laws rather than human preferences, helps calibrate our expectations and responses to cosmic discoveries with appropriate scientific skepticism. Our experience with previous interstellar visitors, the enigmatic Oumuamua with its unusual acceleration patterns, and the well-behaved Borisov with its textbook commentary properties, demonstrates that interstellar objects don't conform to single templates or predictable behavioral patterns. Each visitor tells unique stories about stellar environments, planetary formation processes, and complex physics governing small body evolution across galactic timescales. 3 Atlas adds another crucial chapter to this growing library of interstellar narratives. Its carbon dioxide-rich composition, extreme velocity, and precisely choreographed planetary encounters provide new data points for understanding how objects form around distant stars, survive interstellar journeys, and interact with stellar systems encountered during cosmic wandering. The instrumental advances enabling real-time analysis of 3i Atlas, from Hubble's morphological imaging to JWST's molecular spectroscopy to Cephei's extended atmospheric mapping, represent templates for studying future interstellar visitors. The next object discovered by Vera Rubin Observatory's Legacy Survey of Space and Time will benefit from techniques, protocols, and international coordination mechanisms developed through our investigation of this remarkable wanderer. This technological and methodological progress exemplifies humanity's growing sophistication in cosmic exploration. We no longer simply observe celestial events as passive spectators. We actively investigate them, using instruments capable of measuring chemical compositions across interstellar distances, tracking trajectories with extraordinary precision, and coordinating global research campaigns within hours of discovery. The civic lessons embedded in 3i Atlas research extend far beyond astronomical education. The ability to distinguish established facts from preliminary speculation, to appreciate uncertainty without succumbing to anxiety, and to evaluate extraordinary claims against appropriate standards of evidence, serves citizens well in contexts extending far beyond cosmic mysteries. Media literacy skills required to navigate coverage of astronomical discoveries, recognizing differences between peer-reviewed analysis and sensational speculation, understanding how scientific confidence evolves over time, appreciating distinctions between uncertainty and danger, might just transfer directly to other domains where scientific information intersects with public policy and personal decision-making processes. Perhaps most importantly, 3i Atlas challenges us to expand temporal and spatial perspectives beyond narrow confines of human experience. The object we're studying has traveled farther than human civilization has existed, carrying materials older than complex life on Earth, following gravitational laws operating with mathematical precision across cosmic scales dwarfing terrestrial geography. This expansion of perspective serves as antidote to parochialism, often characterizing human affairs. Political disputes seeming monumental from terrestrial viewpoints shrink to appropriate proportions when viewed against cosmic timescales. International boundaries dividing our species become invisible when viewed from perspectives of objects that have wandered between stellar systems for millions of years. The call to wonder that 3i Atlas represents extends beyond scientific curiosity to encompass our collective response to the magnificent complexity of the universe we inhabit. The carbon dioxide-rich atmosphere surrounding a kilometer-scale nucleus represents simple physics in action. Direct transition of solid ice to gas as stellar radiation warms ancient volatile materials. Yet this simple physics carries profound implications for understanding planetary formation throughout our galaxy, chemical processing in interstellar environments, and cosmic ecology connecting stellar systems across vast distances and timescales. Fear narrows our world, reducing cosmic mysteries to threats while closing minds to possibilities exceeding current understanding. Wonder enlarges our world, opening minds to magnificent complexity of a universe, continuing to surprise, educate, and inspire those brave enough to look up at night skies and ask what secrets might be hidden among stars. 3i Atlas, racing through our solar system at 200,000 kilometers per hour, while carrying news from distant suns, invites us to choose wonder over fear, curiosity over anxiety, and cosmic perspective over terrestrial parochialism. Whether we accept that invitation will determine not just our understanding of this particular visitor, but our readiness for cosmic discoveries awaiting us in decades and centuries ahead.